We're going to look at some gravitation problems, although in this case, I'm not going to do the work from scratch, but I'll rather talk over some work that's already been done. So we've got a question about free fall on planet Rotan. A satellite circles planet Rotan every 5.1 hours in an orbit having some radius. If the radius of Rotan is some other radius, what is the magnitude of the free fall acceleration on the surface of Rotan? All right, well, we're given this planet Rotan and a satellite out here, and we're told something about the orbit of this satellite. Well, the orbit of this satellite exists in circular fashion because the centripetal force equals the gravitational force. So mv squared over r equals big G, big M, that'd be the mass of Rotan, times the mass of the satellite over r squared. Now, this is one place to start, but keep in mind that the centripetal force, the centripetal acceleration, can either be v squared over r or m omega squared times r. And so depending on the information you're given, you might choose to use one or the other. Now, in this case, I used omega squared times r. In this case, I called it d. I guess I'm going to change that back to r. Omega squared r, where the r is the orbital radius where the satellite is. Now, the satellite is orbiting in that way because of the mass of Rotan. And that's really kind of the question is, what is the mass of Rotan? That's sort of the crux to this problem. So we got to solve for the mass of Rotan. That's the key piece of unknown information. So whether you choose to use omega, which would be one orbit divided by the period, or if you want to use velocity, which would be the distance divided by time, which would be 2 pi r. That would be the distance, that would be the circumference of its travel around its orbit, divided by the period, which would be whatever the period is, 5.1 times 3600. Now, either way, it'll work out. Now, in this case, you're given the period, so just a little bit easier to get omega using the period alone. So we got omega squared times r equals big G times the mass of Rotan divided by r squared, and do some algebra, work through, and we find the mass of Rotan. Because really, in order to know the gravitational attraction on the surface of a planet, you need to know only two things about that. You need to know the mass of the planet and the radius of where you are measuring. And so I'm going to call that the radius at the surface. So once we've got the mass of Rotan, then we need to place an object or yourself at the surface of Rotan. And as we've seen before, the gravitational acceleration, or the gravitational field strength, is big G times the mass of the planet divided by r squared, and that r is wherever you are going to be measuring the gravitational field strength. So if we're going to be measuring at the surface of Rotan, then we plug in the mass of Rotan and the radius of the planet itself, and we get the gravitational acceleration at the surface. Problem number 5 is something that would never really happen on Earth, but it's fun to try the mental exercise. So if we've got two masses on Earth, we've got a large mass and a small mass, and we're going to place them near each other such that gravity is going to be great enough to overcome the friction holding them to the floor, preventing them from sliding. So basically, we need to equate the frictional force to the gravitational force, and then solve for a radius. At what distance will those two forces be equal? Or effectively, at what distance would gravity begin to be larger than the frictional force. So we're finding the frictional force necessary to accelerate the 132 kilogram mass. So we put the 132 kilogram mass on the ground, and we've got mg down, we've got normal force up, and if we're going to be accelerating it due to a gravitational force sideways, then the gravitational force needs to equal or exceed friction. So solving for friction, we got the friction is going to be mu times the mass, 132 times gravity times 10. So the frictional force that is going to exist between this smaller mass and the ground is 1980 newtons. So at what distance between the two objects will a gravitational force exist that is 1980 newtons? So we put the two masses into our system and solve for the distance between them. Turns out that the distance between them will be a little bit more than 4/100ths of a millimeter. And that's the center to center distance. Well, the problem with that is that the objects themselves are going to be far larger than that. So there's no way that the centers of the two objects could actually ever be that close, because one object cannot physically pass through another. And so while this could never happen, it's still kind of a fun little exercise. Problem number 7. The challenge here is visualizing exactly what's happening. How far from the center of the Earth must a space probe be along a line toward the sun? So we've got the Earth and the sun, and we're going to put a little satellite somewhere in between so that the force drawing it towards the Earth is going to be equal to the force drawing it towards the sun. So we don't know what that distance is to the Earth, and we also don't know what that distance is to the sun, but we do know what the center to center distance is between the Earth and the sun. So whatever those two are, they got to add up to that total distance. And so we can at least describe them in terms of each other. So that's that right there. The radius of the to the sun, the distance to the sun plus the distance to the Earth is going to be equal to the total distance between the Earth and the sun. And so we've got basically we're setting the two forces equal to each other. The force towards the Earth is going to be equal to the force towards the sun. And we could say that Fg, using Fg, is big G times m1 times m2 over r squared. But note in this case that the force pulling it towards the sun is going to depend on the mass of the satellite, and the force pulling it towards the Earth is also going to depend on the mass of the satellite. And so basically we've taken the ma equals big G, big M, little m over r squared, and canceled that out. So really what we're left with is an equation for the acceleration. So whether we want the forces to equal or the accelerations to equal really amounts to the same thing. And so we are setting those two equal to each other, setting the acceleration towards the Earth to be equal to the acceleration in the direction of the sun. And thus we end up solving for one radius in terms of the other, and then kind of plugging the rest of the way in algebraically. And then we've got a proportional reasoning kind of question. If you're going to change some stuff, how is that going to change some other stuff by a proportion rather than a specific value? We're looking for a fraction. So suppose we could shrink the Earth without changing its mass. So we're going to take the same mass of the Earth, but make it more dense. We're going to squeeze it into a smaller size. At what fraction of its current radius, so we start with the big Earth, and then we squish it into a small Earth. At what fraction of its current radius would the free fall acceleration at the surface be 3 times its present value? Well, its present value is g, and we want the new value to be 3g. So our new gravity prime, is going to equal 3 times what it originally is. Since this is a ratio, we want to find the ratio of g prime to g. We can set them up as a ratio. So we've got g prime relative to g. Well, g prime is going to be based on the new radius, and the original g is going to be based on the existing Earth's radius. So we've got the gravitational acceleration, we're leaning on this formula again. The gravitational acceleration, wherever you are, is equal to big G times the mass of the planet divided by r squared. And so we're setting our g's equal to that formula, and then finding the ratio of one formula to the other. And it so turns out that we want g prime to equal 3g. So the ratio g prime to g is equal to 3. So basically we're setting this whole ratio equal to 3. And so that what emerges from that is setting this whole, I think this whole ratio equals to 3 and follow through algebraically.